Let's talk about conductors versus insulators at this point. This is what you need to be able to do. Tell me the difference between a conductor and an insulator with an example and explain how conduction happens, the particles involved, and how even insulators can be forced to conduct, and recognize the evidence of the breakdown voltage being exceeded and damaging an insulator. And finally, be able to explain how the design of transmission towers across country follows logically from the idea of insulators and conductors. A conductor is an atom that is willing to let go of its electrons. The metals are profoundly good at this, the nonmetals are not. These valence electrons can hop from atom to atom as if these three atoms were islands in the Pacific Ocean and these were the dolphins free to swim about. We call it electronicity or electricity because it is the electrons that can hopscotch from atom to atom. If the protons moved, we would have called it protonicity. Now, some atoms need a bit of encouragement to get the electrons to go out and play. With a conductor, there's virtually no need to give them a shove. These ones need a tiny shove, so we do it by lifting up a ramp until these marbles come out of their rut and they begin to flow. But if it's an insulator, like plastic, the electrons are kind of bedded down. They're not really willing to go outside and play amongst themselves. So we have to lift them to a higher voltage before they will flow. Now, if I wanted this to represent copper, there would be no ruts whatsoever. It would just be a straight, smooth ramp. That would be copper, gold, silver. They're nearly perfect conductors. If they're slightly bedded in like this, that might be aluminum or silicon. So you might need to go to like 4 or 5 volts and suddenly it'll conduct. But this could be like plastic, and those electrons are so stuck in the mud, to get them moving, you'd have to do this. You'd lift the ramp so high. So this would be like the equivalent of going to 100 volts, that finally these things come tumbling out and crash down. Well, that's not very good. That's a full-out avalanche, and it's going to cause damage when that happens. I like to think of this as when you drink a drink with ice in it, say from McDonald's, and you really want to crunch an ice cube, and there's a couple ice cubes stuck to the bottom, so you tip it up in the hopes that you're going to get one ice cube, and they don't move because they're stuck to the bottom, so you tap it, and suddenly you get an entire face full of ice cubes all at once. That's basically a breakdown voltage. You've exceeded the holding power, and you get it all in the face in one shot. Once you break something down and you force the electrons to move, you now have a nice ionized state. And the electrons are now free to move very quickly through the material. So once there's an initial push through the material, then the other electrons can find their way through that pathway. So you see it here with a lightning bolt. The lightning bolt here is quite bright, but if you look, there are these faint lines of electrons that manage to ram their way through the air. And as soon as these guys in the lead here ram their way through the air, there's a stampede behind them. So this is sort of like the lead soldiers. They've cut their way through, and their fellows can now follow that path. So in fact, when you see one lightning bolt, there's often 5 or 6 that follow so quickly you need a high-speed camera to see it. So lightning loves hitting the same place twice. Once that pathway is open, it'll tend to keep taking it. This gives us some great power. If we know the insulating capacity of a gap, then we can measure the voltage by simply measuring the gap that's jumped. So let's say there's an air gap here, and we've measured that the air gap has a strength of 5 volts per centimeter. This is called the dielectric strength, not testable. If there's a gap of 1 centimeter here, then you're going to need 5 volts, which is basically like saying 5 joules of energy for these electrons to jump the gap. Well, they got 6 volts, so these ones have more than enough to jump that gap. But if we make the gap 3 centimeters wide, that would give us an insulating power of 3 times 5, 15 volts. These are 12-volt electrons. They cannot jump the gap. So you could bring this point closer, and at the moment the spark jumped, you could measure the distance, and knowing the insulating capacity, you could tell me the voltage. And here's an example of this. This is acrylic, which has an ability to insulate to 250,000 volts per centimeter. This plastic is 4 centimeters across, so 250,000 volts a centimeter for 4 centimeters, that's 1,000,000 volts of insulation. So the spark that you see petrified in the plastic was 1,000,000 volts to do that. And it exceeded the breakdown voltage of the insulator and destroyed it along its pathway. So those are tiny little tubes where the plastic was vaporized. The acrylic is destroyed there, but it's a really beautiful pattern. If you get hit by lightning, your skin may show such a pattern on it. If lightning hits sand, which is a really good insulator, you will discover that the sand has been melted similarly into this Lichtenberg figure, but they call it a fulgurite. Here's one freshly dug up. Here's one that's been cleaned off, and you can see the pathways the electrons burned through the sand, turning it to glass. The big question is, what on earth are frozen lightning strikes like this doing in that desert in Libya? Now we can turn our attention to these towers we see across country. Why do they look the way they do? Why are they so high? And what are these sort of like ornaments hanging off them? Well, it has to do with rubber. Rubber's a good insulator, but if you work out how much rubber those wires would need to give you 250,000 volts insulation, the wires would be encased in very thick rubber, and the weight of them would be huge. They'd tear themselves apart. So instead, the wires are bare naked, and they're kept high enough above the ground that there is no chance, even on a rainy day, of the spark jumping to ground. They are kept far enough away from the towers that there's no chance of a spark jumping this way. And if we take a good look, what we've got here are glass trees, and it's attached to the cable. This is an insulator, but also notice bare metal here, and they put a basic insulation jacket here. It's not perfect. That is no way that jacket is shielding 250,000 volts, but it helps. But this is all non-conductor. Why this disc shape? Because you don't want water during the rain making a nice clean path to this. And that provides you the insulation gap you need to avoid having arcing between the tower and the wire. So let's take a look at air. It can block 3 million volts a meter. Glass can block 20 million volts a meter. The tower is designed for 250,000 volts. If you look at the dimensions of the tower, you can tell me if the insulation trees are good enough. So if we look right here, there's your gap, 3.7 meters. Round it to 4 meters. They've put these trees 4 meters apart. Okay? At 4 meters apart, how much insulation do they have? And is it enough that the 250,000 volts in the wire will not jump through that glass? And if you can do that, you know everything you need to know about insulation. And then you work on this assignment here, and we'll take it up later. There endeth the lesson.